Topic 9: Nuclear and Particle Physics. In this chapter, there are 3 subtopics altogether. However, we are just going to focus on 2 subtopics in tutorial. First subtopic is binding energy and mass defect, and second subtopic is radioactivity. In 9.1, we're going to learn how to use the equation for mass defect, where delta M is equals to ZMP plus NMN minus M nucleus. Okay, so I want you to take note. There's a slight corrections in your books. Your books give you the equations with a negative sign right here. So I want you to change it into a positive sign. The correct equation should be delta M equals to ZMP plus NMN minus the mass of a nucleus. And then we're going to learn how to use the binding energy, EB equals to delta MC squared. And then determine binding energy per nucleon. Now, why is it important to know how to calculate the binding energy per nucleon? Because it will tell us whether a particle is stable or not. And then last, sketch and describe graph of binding energy per nucleon against nucleon number. Before we proceed to the question, now let us see what is mass defect and binding energy. So the key idea in mass defect is very simple. Let's look at the diagrams right here. So when it comes to mass defect, it tells you that there's a difference in mass between the nucleus and the nucleons that make up of it. Okay, so if you look at this diagram now, it tells you that this one nucleus, the mass is smaller than these 7 separated nucleons that make up of this nucleus. Okay, that is because some of the mass has been converted into energy that is required to bind the protons and neutrons together. So when it comes to separated nucleons and nucleus, it has smaller mass because part of the mass has been converted into energy. So now if you want to split this nucleus back to nucleons, then what are you going to do? You need to add the same amount of binding energy into the nucleus to break it apart. Therefore, binding energy is defined as the energy required to break apart a nucleus, so that it goes back to its separated nucleons right here. So how are we going to calculate mass defect? Well, like I mentioned just now, mass defect is the difference in mass between the nucleus and the separated nucleons. Therefore, mass defect delta M can be calculated by using ZMP plus NMN, which is the sum of the mass of the separated nucleons minus the mass of the nucleus. And then how to calculate binding energy? We calculate it by using EB equals to delta MC squared. Now, when it comes to the first equations right here, these equations delta MC squared, we use everything in SI unit. Okay, but when it comes to this chapter, for mass, we seldom use kg. Quite often, we use the atomic mass unit, okay, which is AMU. Or when it comes to calculations, the unit is U. So if you're going to use delta M in U, then you use these equations where EB straight away is equals to delta M times 931.5 MeV, mega electron volt. So the derivations you can go through your lecture notes, okay? And one last thing before we proceed to the question. Now let us go back to the mass defect equation. Mass defect equation, this equation, it's all about nucleus. But quite often, question will give us atomic mass. So if you are going to calculate mass defect by using atomic mass, then what should you do? You need to calculate the mass of a nucleus first. How to calculate the mass of a nucleus? You can calculate M nucleus by using M atomic. Now, atom is a particle that consists of electron, therefore minus the mass of the electron, ZME. Okay, ZME. Then you will obtain the mass of a nucleus. So once you have the mass of the nucleus, you can then use it to calculate mass defect. by using the equations given right here. So that is mass defect and binding energy. Next, how are we going to tell whether a nucleus is stable or not? Then we have to refer to this graph. Okay, so this graph, we have y-axis, binding energy per nucleon, and x-axis mass number. Now the values of binding energy per nucleon, which is EB over A, it tells us whether a nucleus is stable or not. If the value is larger, then it is more stable. If the value is smaller, then it is less stable. So let us go back to this graph. So just now I say the value, it tells you whether the nucleus is stable or not. If the value is larger, then it's stable. So if you look at this graph, the largest EB over A, it falls within this region, in between mass number 50 until mass number 80. So this region, we call it region with greatest stability. So any particles that drops inside this region is very stable and they are unlikely to undergo a radioactive decay. So how are we going to determine which one is more stable? Then you look at whether they are closer to this region or they are far apart from these regions of greater stability. So for example, if you compare this Ag and this, let's say, uranium. Now uranium is far away from the regions of greater stability. Therefore, uranium is less stable compared to Ag. So that is how we determine which one is more stable based on the graph, if you are not given the value. But if you can do the calculation, that would be the best. Exercise 1. The most abundant isotope of helium has a 4,2 helium nucleus whose mass is 6.6447 times 10 to the power of negative 27 kg. So for this nucleus, find the mass defect and the binding energy. Now one thing that you have to take notes, you are given the values of a constant m proton and m neutron in kg. Therefore, you have to stick to kg in your calculation. You have to use the values given right here, not the value in your list of constant. If you are not given the values in the question, then it is up to you whether you want to use atomic mass unit or kg in your calculation. But if you are given the value in the question, then you have to stick to the values given. So questions A, mass defect. Well, this question is very simple. Why? Because you are given the mass of a nucleus straight away. Okay, so questions A, mass defect delta M is equals to ZMP plus NMN minus the mass of a nucleus. Then straight away you can get the answer in kg. Now since your mass defect is in kg, when it comes to binding energy, then we are going to use the one with SI unit. Now what does it mean by with SI unit? Well, it means you don't use the equations EB equals to delta M times 931.5. You use EB equals to delta MC squared, where your delta M is in kg, and then C squared is 3 times 10 to the power of 8 ms negative 1 squared. Okay, the speed of light, that is the values of C. Then eventually you will get the value in joule. Okay, so it's not in MeV, but it is in joule because you calculate the value by using kg and also ms negative 1, which is SI unit. Therefore, your final answer should be in SI unit. So that is questions 1. Exercise 2. The atomic mass of helium 42He, it's 4.0026 U, and the atomic mass of hydrogen 11H, it's 1.0078 U. Using atomic mass unit instead of kilogram, so questions want you to use unit U to obtain the binding energy of helium nucleus. So given M neutron is 1.0087 U, and the atomic mass for a hydrogen 11H is 1.0078 U. Now what you have to take note is the values given right here is the atomic mass for hydrogen, which is the mass that consists of, that includes the mass of a electron. Okay, so what does it mean? Now we know hydrogen, it comes with one proton, and the values given right here, it consists of the mass of one electron. So which means this value given right here, it's actually the values of MP plus ME, 1 MP plus 1 ME. Okay, and then let us go back to the questions. Now in the original questions, you are given the atomic mass of helium. So how are we going to calculate mass defect? Well, since we want to calculate binding energy, mass defect is a must, right? So how are we going to calculate mass defect? Now, if you recall the key idea that I mentioned just now, if you are given atomic mass, then you should calculate M nucleus. But when it comes to exercise 2, this question is a bit special because you are not given the mass of the proton. You are given the mass of a hydrogen, the atomic mass. And if you are given this value, then you have to use it in this question, like I mentioned in the previous question. Okay, so any constant values given in the questions, they want you to use it. So you have to use the values given. You don't use the M proton from the list of constant. Okay, remember that. You have to use the atomic mass for hydrogen. So how are we going to use atomic mass for hydrogen? Well, let's go back to the original equation for mass defect. So delta M equals to ZMP plus NMN minus M nucleus. That is what we have. If you don't want to use M nucleus in the equation, if you want to use M atomic straight away, then you can actually modify these equations a little bit. It becomes delta M equals to ZMP plus ZME plus NMN minus M atomic. Okay, so what is the difference between M nucleus and M atomic? Now, M atomic, it comes with the mass of electron, sorry, okay? It comes with the mass of electron. So, if you're going to use M atomic, then you have to take into considerations the mass of electrons in the nucleon before you add all of them together. Okay, so when it comes to this question, how are we going to solve it? So you are given atomic mass of helium. So this helium, it consists of 2 protons. Okay, now to become neutral, if it has 2 protons, then it must also come with 2 electrons. Okay, that is if you want to get an atom that is neutral. So 2 protons must come with 2 electrons. So how are we going to put it in our equations? Well, ZMP plus ZME. If you factorize the Z out, you will get ZMP plus ME. Isn't it looks familiar to you? Well, it is, because that is the atomic mass for hydrogen, MP plus ME. So this equation, actually, it can be written as delta M equals to Z M for what? For hydrogen. Okay, the atomic mass for hydrogen is the mass of 1 proton and 1 electron. So Zm hydrogen plus NMN minus M atomic. So from here, you can then get the mass defect in atomic mass unit. Once you have it, you can then calculate the binding energy by using EB equals to delta MC squared. Now, since your M is in U, therefore now you can use EB equals to delta M times 931.5 MeV. So the final answer is going to be in MeV. So that is how you solve exercise 2. Exercise 3. Rank the following nuclei in ascending order according to the binding energy per nucleon, which is smallest first. So you have phosphorus, 3115b, cobalt 5927co, tungsten 18474w, thoriums, where you have 23290th. Now, questions ask you to rank. Okay, so when it comes to these questions, you don't have to do calculations, because if you're going to do calculations in the exam, it is quite, I would say, not practical, because the calculation is going to be very long. Okay, because you have 4 different particles right here. So if you're going to calculate binding energy per nucleon for 4 of them, then it's going to be very long. So how are we going to solve it? You have to refer to the graph of a stability. Okay, so remember the things that I mentioned just now. So when it comes to the graph of stability, in between 50 until 80, this is the regions of greater stability. So if you have any particles where the nucleon number is located in between 50 until 80, this region, then that is most stable. So in this case, the most stable one would be cobalt, because it has a nucleon number 59, which is located inside the regions of greater stability. So this is the most stable. And then the second one, well, if you look at the other 3, this one is 31, 184, 232. 31 is somewhere right here, and then 184 is somewhere here, okay, which is less stable compared to 31. And 232 is even not stable compared to the W, the tungsten. So you have to look at the positions, roughly where is it? Okay, so based on this graph, obviously the most stable one is the cobalt, followed by phosphorus, and then tungsten, and the one that is not stable at all is the thorium. And since the question asks you to state the value of a binding energy per nucleon from the smallest value, then it's going to be thorium, and then tungsten, and phosphorus, and the most stable one is the cobalt. Remember, the one with larger value is the more stable one. So since cobalt is the most stable, then it has the largest value. So from smallest to largest, you start off from thorium and then until cobalt. So that is the answer for questions 3. Exercise 4. Calculate the binding energy per nucleon of a neon 20 nucleus. So this one it should be 20, 10, and E. Now this question is asking for the answer in 2 different units, joule per nucleon and MeV per nucleon. Okay, so usually you can do the unit conversions after you obtain the values of binding energy. So given the atomic mass, so once again you are given atomic mass of a neon, so 20, 10, and E, equals to 19.992435 U. Mass of neutron in 1.008665 U. Mass of proton 1.007277 U. Mass of electron 5.49 times 10 to the power of -4 U. Speed of light in vacuum 3 times 10 to the power of 8 meters per second. So calculate the binding energy per nucleon. So when it comes to this topic, actually the rules is very simple. Okay, it's always start from delta M, and then you calculate EB. So if questions wants binding energy per nucleon, then once you have EB, you calculate EB over A. Okay, so that is the flow. So you have to start from delta M. So how to calculate mass defect? Now be careful. This question, you are not given the mass of a nucleus, but you are given atomic mass of a neon. Okay, atomic mass of neon. So when it comes to this question, okay, what are you going to do? Let's calculate the mass of a nucleus first. Okay, the mass of a nucleus, M nucleus, it's equals to M atomic minus ZME. Okay, so remember the numbers of an electron is always same as the numbers of proton. Therefore, we have a ZME right here, where Z is also equals to 10. because you have 10 protons in this neon. So once you have mass of a nucleus for a neon, you can then calculate mass defect by using ZMP plus NMN minus M nucleus. Okay, minus M nucleus. Now, of course, you can also use ZMP plus ZME plus NMN minus M atomic. Both are accepted. Okay, as long as you got the right unit. So delta M, you should got it in U, because questions give you the unit in atomic mass unit. Okay, so you're given U right here, U right here, U right here, U right here. So delta M, the unit should be in U. Okay, so once you have the unit in U, okay, you can then proceed to calculate the binding energy. Now, do you have to convert delta M into kg? No. Why? Because question is just one binding energy per nucleon in 2 different units. Okay, it didn't ask you to calculate mass defect in 2 units. It didn't ask you to calculate binding energy in 2 different units. What it wants is just binding energy per nucleon in 2 different units. Therefore, for mass defect, you can leave it in U. That is fine. Okay, so once you have mass defect in atomic mass unit, you can then calculate EB by using delta MC square, which is then equals to delta M. Now this C square is 931.5 MeV. Okay, and then it is equals to answer in MeV. Okay, it is equals to answer in MeV. So once you have EB in MeV, okay, now you can convert the EB into joule. Okay, so EB equals to, you do the unit conversions and get it in joule. Alright, so delta M, you don't have to convert it to kg. Okay, you convert it into a joule after you got EB. So once you have EB in MeV and EV in joule, you can then calculate EB over A in MeV. Okay, so EB over A. If you use the E in EB in MeV, then this one would be MeV per nucleon. And then you repeat it again by using E in joule. Okay, then you are going to get the value in joule per nucleon. Right? So that is how you do it. So unit conversions, you try to think how to solve it. If you don't know how to do unit conversions, you may refer to the example in your lecture notes. So that is how you solve questions 4. Exercise 5. The binding energy per nucleon of a lithium-6 nucleus, so here it should be 63Li, is 5.33 MeV per nucleon. Okay, this is the value for per nucleon. So find the mass defect of the nucleus in kg. So this question, it wants you to do it the other way around. Okay, it doesn't want you to calculate binding energy per nucleon, but it asks you to start from binding energy per nucleon and then you go backwards to get the mass defect. So EB over A given is 5.33 MeV per nucleon. From here, you then calculate EB. Now, can you calculate EB? Yes, you can, because you actually have the values of nucleon in the questions, where the values of nucleon is the 6. Okay, your values of A is given in a question, which is in this symbol 6. So from here, you then get the EB in MeV. Okay, so since it is in MeV, what we do know is EB is equals to delta M, now MeV, right, times 931.5. So from here, you then calculate M, and this one, the unit should be in U. But don't forget that question is asking for the unit in kg. Therefore, once you got delta M in U, you then have to convert it into kg. So that is how you solve questions 5. Exercise 6. Which among the following nuclei is likely to be more stable? Okay, so once again, if the question is asking about the stability, then it is asking for EB over A. So given helium 4 nucleus, so it should be 4,2He, and chromium 52 nucleus, which is a 5,224Cr. Give an explanation by referring to the binding energy per nucleon. So when it comes to this question, obviously it wants you to do the calculation because it asks you to refer to the binding energy per nucleon for these two particles, these two nucleus. So what are you going to do? Basically, you just have to do the calculation for 4,2 helium, and then you repeat the calculation for 5,224 chromium. Okay, so you start off from delta M, and then you calculate the EB. After that, you calculate EB over A. Once you have the value, you then compare the values of the binding energy per nucleons for both of them and see which one is greater. The one with larger value is more stable. So in this case, the binding energy for chromium is actually larger than helium. So if you got it right, the answer should be, this one is 8.54 MeV, and then this helium, it should be 7.075 MeV. Okay, so try it yourself and see whether you can get the answer or not.